It's June 12, 2025. Air India Flight 171 sits on the tarmac in Ahmedabad. At 36 degrees Celsius, it's a scorching day, and the Boeing 787 is heavily loaded, weighing in at over 200 tons. The high temperature thins the air, meaning the aircraft will need nearly the entire length of the runway to generate enough lift for takeoff. From the ground, the initial climb looks perfectly normal. But seconds later, at a meager altitude of just 55 feet, both engines completely shut down. Deprived of thrust, the heavy aircraft immediately begins losing altitude. It sinks rapidly toward a dense neighborhood just past the airport perimeter, striking the buildings and disintegrating into fragments in exactly 2.5 seconds. When investigators pulled the data from the wreckage, they found a specific, terrifying input. The flight recorder showed that the cockpit fuel cutoff switches had been moved to the off position. Modern aviation is built entirely around redundancy. Jet engines operate independently of each other. Two healthy turbines simply do not simultaneously flame out in the exact same second without a direct, verifiable cause. To understand how this was possible, we need to investigate the systems that control these engines, separating mechanical failure from software errors and the actions of the crew. The official preliminary report lays out a very specific sequence of events. It claims that the plane hit a maximum speed of 180 knots, and immediately after reaching that speed, the engines were cut off. But we have a way to test that claim. By taking airport security footage of the crash and stabilizing it frame by frame, we can build a 3D simulation that tracks the exact physical location and speed of the plane at every fraction of a second. This graph compares the official report's timeline against the data from that 3D simulation. The physical evidence shows a glaring anomaly. The plane continued to accelerate for 5 full seconds after the official report claims the engines were shut down. The physics of a jet engine flameout are entirely predictable. The moment the fuel supply is cut, all remaining high-pressure gases flush out of the turbine in under 1 second, causing the thrust to collapse. There is absolutely no residual energy left capable of pushing a 200-ton aircraft faster for 5 seconds. Because the official timeline violates the basic laws of physics, we cannot accept its surface-level narrative. We have to independently verify exactly how those fuel switches were triggered. Let's start with the first possibility. Did the engines fail on their own and the data recorder simply registered a false signal from the switch? This schematic shows why a false signal is impossible. The Boeing 787 uses a single, dedicated data wire running straight from the physical switch to the recorder. Every single second, the computer takes a hard mechanical reading. So could software have moved it? The 787's TCMA safety system can cut power, but it bypasses cockpit switches entirely, instead closing a valve deep inside the engine. Furthermore, once the TCMA software shuts a valve, it locks out the crew. The engines cannot be restarted in the air and require a ground maintenance crew to reset. Yet the flight data proves that someone successfully switched the engines back on seconds before impact. The software didn't do this. That brings us to the cockpit itself. During a turbulent, high-speed takeoff roll, could a pilot have simply bumped both switches by accident? Look closely at the fuel control switches on the center console. They are spring-loaded. To move them, you have to deliberately pinch the cap and pull upward against the spring tension before sliding them down. They also sit behind raised physical guards and feature mechanical stops near the base. This deliberate design makes it physically impossible for a stray hand to accidentally bump and activate both switches within a 1-second window. With data errors, software overrides, and accidental bumps ruled out, the facts leave no other explanation. The fuel was shut off by a deliberate action in the cockpit. The data from the final moments reveals a frantic response. Realizing the fatal error, a pilot reached down and desperately moved the switches back to the run position. But turbines require time to spool down and spool back up. During that critical delay, gravity took over, and the massive, heavy aircraft began dropping rapidly toward the ground. This diagram illustrates why the crew never retracted the landing gear. Standard procedure mandates that pilots must verify a positive rate of climb, meaning the plane is safely gaining altitude, before lifting the wheels. Because altitude loss made that impossible, the extended gear remained locked in place, adding massive aerodynamic drag to a plane already falling. We now know exactly how the flight ended. The fuel was manually and intentionally cut in the cockpit. But that mechanical certainty collides with human logic. The captain and first officer had over 19,000 combined flight hours. For a veteran crew to intentionally shut down two perfectly healthy engines during a critical climb defies reason. Forensic data can pinpoint the exact moment of a failure, but it cannot explain the human reasoning behind it. We know how the engines died, but the reason why and the physics of that 5-second acceleration gap remain open questions. I'm curious to hear your theories on that gap in the comments below.